So chapter 22 is all about alpha carbon chemistry. I kid you not, I took a class in grad school where it was a whole semester on this one topic. You can spend a lifetime studying alpha carbon chemistry. But we're just going to kind of go over the basic reactivities for sophomore organic chemistry. Let's define what alpha carbon chemistry is, though. Whenever you're looking at a carbonyl, chemists like to classify the carbons based on how far away they are from that carbonyl group, right? And we use Greek letters to differentiate. So this one carbon, that's one carbon away from the carbonyl, is our alpha position. And it's quite reactive. What do you think the next carbon over is?
Beta.
Beta, yeah. I'll check your Greek lettering here. Next one? Gamma. Next one? Delta. All right, so we can start using this terminology anytime we're talking about carbonyl groups to differentiate the carbon and its position to the carbonyl. If we think about normal alkanes, does anybody know what the pKa is of most CH bonds? Are they very acidic, a normal CH bond? They're really, really weakly acidic. Usually you can't even deprotonate them if you try, right? They typically have a pKa of about 50. However, if we look at the protons coming off of the alpha position, they're remarkably acidic. In fact, they're usually about 20. So we're talking about 30 orders of magnitude different. Does anybody have an idea why? Yeah, I heard it in the back. Resonance, right? Whenever you don't know the answer is resonance. Makes you sound smarter. You might not want to use it in your math class, though. Let's take a look at why this is the case. And we'll just do a basic reaction with a strong base. And we'll take just a really simple ketone. We'll use acetone, and I'm going to draw in the set of protons on the right. And our generic base, that's B-. This base can grab really any of these protons, and it can kick down electrons onto this carbon. And I'm going to show this with equilibrium arrows. That gives this carbon a formal negative charge. And then we know that we can delocalize this negative charge all the way up to the oxygen. We did this back in first term. And we can bracket these. Does anybody remember what this is called, the compound on the right? It's an enol, but we've removed the proton from the enol. So what do we typically call something if it has a proton removed? What's the suffix? I. So think about carboxylic acid. What do you call the salt of a carboxylic acid after it's been deprotonated? Yeah, an enolate. So we put on the suffix ate to indicate that it has a negative charge. So this is called an enolate. These do really unique chemistry, and we're going to spend a good chunk of the chapter talking about this. The neat thing is you can form these using catalytic acid or base. We saw this in our chapter when we covered alkynes. So let's briefly review this. So reaction with catalytic acid. This was what we saw when we were doing our hydration of alkynes. However, let's take a look at it with the reverse mechanism. If we've got catalytic acid around, what do you think the first step's going to be? Protonate the carbonyl, right? We saw that pretty frequently last chapter. pick up electrons. Now this oxygen's got a formal positive charge. We've got water around. And water will abstract one of these alpha protons, so I'll draw them in. And it will kick up electrons. It's catalytic because at the end of the reaction we're regenerating the acid that we used. Does anybody remember whether or not the ketone side is favored or the enol side is favored? Ketones almost always favored. However, there are some exceptions, and we'll talk about that more this chapter. However, even if something's only present in less than 1%, that can still be very significant in terms of reactivity. So in this reaction, we could form a trace amount of enol when we treat acetone with an acid. It won't be very much, but it will be enough to continue on and do unique reactions. We can do the same thing with catalytic base. So this time, the first step will just be deprotonation of an alpha proton. So I'll do hydroxide as our generic base. This can clamp down. Actually, let's draw out all the resonance structures. And we know that this will form our enolate like we saw above. So I'll bracket these in. And then we also generated water in this step. And under this condition, our enolate can grab a proton off of water. Let me slide over here. And we can form our enol using base too. And we regenerate our base, which makes this reaction catalytic. Yep.
Just a quick question. So each of these molecules really has two alpha protons, right?
Yes.
Okay. So
Yeah, you could pick either side. In this case, it's symmetric, so it doesn't really matter which side you pick for the alpha proton. It gives you the same product. There will be some cases, though, where you've got unsymmetric ketones, where you might get a mixture of products, and we'll talk more about that a little later on. So let's take a look at the overall equilibrium for some of these. And I want you guys to help me estimate which side of the equilibrium is most favored. So let's think about this versus the enol. We could form the enol using catalytic acid or catalytic base. It doesn't really matter, but do you think we're going to favor the keto form or the enol form? The keto form. In fact, I told you guys when we were covering alkynes that you can really just show the reaction as one-way arrow, because under most conditions it's almost exclusively going to form your ketone. And in fact, if you go through and you measure this, it's present at 99.99%. So that's why I was saying you can use one-way arrow under most circumstances. However, let's take a look at some odd ones. Let's do this one. Which alpha protons do you think are going to be most acidic? Yeah, the center ones, right? Because of induction and resonance, right? So let's draw the enol that would result. So I'll just arbitrarily pick the one on the left, or sorry, the right, to form our enol. And let me actually change this around. I'm going to actually draw out the OH bond there. Now, which side of the equilibrium do you think is most favored? The enol. Why do you think the enol is more favored? Hydrogen bonding. So that's one reason. So if you look at it, it can actually form the 6-membered ring through intramolecular hydrogen bonding. That's one reason. What's another reason that we don't have in the top example? Yeah, more resonance. And if we look at it, this is a conjugated system, right? We've got alternating double, single, double bonds. We said a few chapters ago that that enhances the stability of compounds. So if you look at these, it really depends on the solvent that these are in. But this is present usually 70 to 90%. So this equilibrium arrow actually favors the right-hand side mostly. And we typically get 10 to 30% of our keto form. And this is due to conjugation and intramolecular H bonding. All right, let's take a look at one last example. This one's also from the book. So this one on the right has conjugation in an alpha and beta position, right? So we would call this, an alpha beta unsaturated ketone. It's also conjugated further out, but let's draw the enol form. Which side do you think is going to be most favored? The right. Not only because of conjugation, but because of what else? Resonance and aromaticity. Yeah, so in this case, aromaticity is the main driving force for this. In fact, if you try to measure this, it's going to be over 99.99% on the enol side, just simply because forming that aromatic ring is incredibly stabilizing. So aromaticity can also change things. What was that? All right, let's take a look at some really basic reactivity of enols and enolates. So let's draw out both forms. We'll draw out one where the carbon's got that negative charge, and we know that this is delocalized so that the negative charge can also be on the oxygen. These are both considered enolates, right? Because we've got a negative charge on there. If we have some sort of electrophile around, we can have an attack either at the carbon or at the oxygen. So let's just draw a generic arrow pushing. We could have attack there, or we can have an attack there. Oops, thank you. Sorry, I've got them upside down. There we go. Let me actually keep the E's blue. Which one do you think's usually observed? The top one or the bottom one? Usually the top one. However, there are some examples where you can actually get, whoops, sorry. I got these all mixed up. There we go. This shouldn't have a positive charge. We normally observe the one at the top. However, under certain circumstances, we actually do get reactivity off of the oxygen. We'll talk more about this as the term goes on, but it's important to remember that both sites can act as the nucleophilic site, either the oxygen or the carbon. Before we go on, though, we're going to talk more about choosing bases because I think a lot of us are a little rusty on acid-base chemistry. So let's do how to choose an appropriate base. All right, let's take a look at this example. And I'm only going to draw one of the alpha protons coming off of acetone. And I'm going to draw a generic base. And this base will have a negative charge. And we know under equilibrium conditions we can form our enolate, right? If we look at this, we need to identify our acids that are present in equilibrium. So in this case, this proton could be considered an acid on the left side, and then we've got our conjugate acid over here. Right? So normally we don't think of ketones as acids, but in this case it's the thing donating the proton, so it is. And we can go through and we can measure the pKa or look it up, and the pKa of acetone is approximately 19.2. If we want this reaction to go to our enolate, should our conjugate acid have a higher or a lower pKa? Oh man. Well, let's think about this, right? Does low pKa mean strong acid or weak acid? Stronger acid, right? So in this case, the stronger acid is going to push the equilibrium to the other side, right? So if we want to form the enolate, we want to pick something where the conjugate acid of the base is pretty high, right? So let's make a little note of this. If we want to favor the enolate, must use a base where the conjugate acid has a higher pKa. So let's think about this. Could we use hydroxide in this example? So let's say sodium hydroxide. What's the pKa of the water? About 15, right? So if we think about water, if we use sodium hydroxide, is actually a stronger acid, and it will favor going straight back to the ketone. So in this case, we have to use relatively strong bases, meaning bases that are stronger than sodium hydroxide, in order to get a substantial amount of your enolate. Typically, the rule of thumb is you want to pick something where the pKa difference is 5 or greater in order to really drive formation of your enolate. So you want to pick something where the difference isn't really small. You want it to be somewhat substantial. Let's take a look at a few of these examples. I've got this ketone, or diketone I should say. Do you think this will be more acidic or less acidic than acetone? More, right? Because we said the conjugate base is very, very stable. In fact, the pKa for this is about 9. And let's consider using sodium hydroxide now. We could draw out the enol form. Right? And then our conjugate acid we said is water. pKa of water we said is approximately 15. So will this favor the enol or the ketone? The enol, right? Because in this case, the pKa of our conjugate acid is much greater, so the equilibrium is going to really favor the right-hand side, and it could favor a small portion of the left-hand side. So if you do have a ketone with relatively acidic alpha protons, you can get away with using sodium hydroxide. However, regular aliphatic ketones, you've got to use a stronger base. I'll show you guys a really commonly used base for normal aliphatic ketones. This nitrogen has a negative charge, and then normally it's the lithium salt. Does anybody remember the name of this base? Starts with lithium. We've got two isopropyl groups, and then it's a nitrogen with a negative charge, so we call those amides. So lithium diisopropyl amide. Propyl. This is a mouthful, so most chemists just call this LDA. LDA is one of the most commonly used bases because it's a really crummy nucleophile. Why do you think it's a crummy nucleophile? Yeah, it's too big. It's not going to add into that carbonyl group very well. However, it's very good at plucking off protons. So if we look at this, we could draw the enolate now. And now we've got our protonated LDA, which is neutral. And we said the pKa of this one was 19.2. Does anybody have a ballpark range for the pK of amines? 36. Looks like somebody's got the book up. So the pKa of amines is typically around 30 to 40-ish, typically right around 35, depending on the amine. So in this case, the pKa of our conjugate acid is much, much, much higher, which means that LDA is an incredibly good base for almost every single reaction. All right, so now we get to get into more interesting chemistry. Oh, thank you. That would have been bad. There we go. So in a way, this could almost be drawn as a one-way arrow because the difference in pKa's is so huge that really it's no longer under equilibrium conditions. It's almost exclusively enolate. All right, let's take a look at the first reaction from chapter 22. This is alpha halogenation. It's a pretty straightforward reaction. And we're going to first do this under acidic conditions. All right, so I'll first start with the overall reaction. The overall reaction involves treatment with catalytic acid. So I'll just write H3O plus. And then usually some halogen like bromine. And if you do this, you get bromination at the alpha position, which is pretty useful. Because if you think about this, you could treat this with a base, and then what do you think you'll get out? We know bromine's a good leaving group. We've got a good base. E2, right? You can do E2 elimination anytime you've got a good leaving group and a good base, right? And we're going to talk more about this later on this term, but you end up forming these really, really stable alpha, beta unsaturated ketones. And alpha halogenation is one of the ways you can go about forming an alpha, beta unsaturated ketone. So let's take a look at the mechanism. Let's put a little E2 under here since some people forgot about E2 chemistry. Let's do the mechanism. So we've got catalytic acid around. We know if we've got a carbonyl oxygen, we can protonate it with catalytic acid. This is under equilibrium conditions, so I'm going to show it with equilibrium arrows. All right. Now what will happen? Yeah, steal a proton from the alpha position. We saw that using our generic acid catalyzed reaction. So this can come grab either one of these protons, doesn't matter. Clamp down. And actually, I'm just going to go straight to the enol and kick up electrons onto the oxygen. And let's just make a little note that this is our enol, and then we regenerate our acid. Okay, now that we've got our enol in solution, we can treat this with our bromine. We've got an alkene, right? We know alkenes can act as nucleophiles. In this case, do you think we're going to form a bromonium ion? So in chapter 9, we saw if you have an alkene and Br2, you form that 3-membered bromonium ion. In this case, not so much. Because what will happen is you've got negative character on this carbon, right? So that carbon's much, much more nucleophilic than the carbon next to it on the other side of that alkene. So this oxygen will actually donate its electrons down, and then this pi bond will hop over, grab a bromine, and kick off a bromide. And then in the next step, we've got water around. This water can grab this proton and then give us our neutral product. And we regenerate our acid. So pretty straightforward mechanism. In this case, we're reacting the carbon instead of the oxygen as our electrophile, or as our nucleophile. Yep.
We always end up with the enol intermediate.
Yeah, usually the enol's the active intermediate that's acting as the nucleophile, right? So enols have partial negative character on the oxygen and the carbon. Usually it's the carbon acting as the nucleophile and attacking some sort of electrophile. In this case, our electrophile is just Br2. One problematic thing with this reaction is that oftentimes this will result in over-halogenation. So it can be somewhat challenging to stop at 1 alpha bromination. So you can repeat this mechanism and actually install 2 bromines.
Would that install on both sides?
Yeah, you could even have it go on and attack the other side as well. But the main thing is once you pop 1 bromine on, that actually makes that carbon even more reactive than it was before. So usually you'll do 2 on one side and then you could over-halogenate on the other side. All right, let's take a look at an example problem. All right, for this example problem, we've got a 5-membered ring with a ketone. We're going to treat this with H3O plus that's catalytic, and we're going to treat it with bromine. Let's try to predict our major product that will come out. And in this case, let's just assume monohalogenation. I'll let you guys try to work on this for a second. Try to draw out the mechanism too.
Do you have to number those steps or not?
Do what?
Do you have to number those steps or not?
Number them?
Yeah, you can put it all together.
One or two.
Oh, sorry. I understand what you're asking now. So this is a one-pot reaction, meaning you're mixing acid and bromine together. You don't need to differentiate it as step 1 and 2. In fact, you don't want it to. Yeah. Yep.
Is there a way we can use to stop this at deprotonation, or is that not just?
Oftentimes, at least in sapling and in the textbook, you can assume monohalogenation unless otherwise specified that you're using a huge excess of bromine. Yeah. So the question we're asking is, will the bromine install at this position, or will it install at the position on the left? Does it matter? Will they result in an equal mixture, an unequal mixture? What do you guys think? All right. Well, let's draw both possibilities. So one possibility is the bromine reacts at that green position. The other possibility is that it reacts at the blue position. There's a couple arguments we could make, right? So the people that pick the reaction at the blue position could say, well, that carbon's pretty sterically crowded. You could have a hard time fitting in a bromine at that site. On the alternate side, you could say, well, that bromine's getting added to the more substituted carbon. We know that the more substituted carbon is typically more stable. Well, let's take a look at the mechanism and try to dig into this in a little bit more detail. So we know under acidic conditions, I'm just going to go straight to our enol. You could have an enol that looks like this, or you could have an enol where the double bond's on the other side. Right? Both of these are enols. Which one do you think's more likely? The first one, why? Oh. Alkene's more stable, right? So we're going back to old chemistry. Over here we've got a tetrasubstituted enol. Oops. This one is only tri-substituted, which means that it's less stable. So using this, we know that the main intermediate will result in bromination at this carbon, right? Which means that this will be our major product and this will be our minor product. So let's just finish up this mechanism really quick. We could have this oxygen clamp down, this oxygen attack the bromine, or we could have this oxygen clamp down and this carbon attack the bromine. And then last but not least, I'm just going to do minus H+. And we get to our major product on the left and our minor product on the right. So in this case, it's not a matter of sterics, it's actually a matter of the stability of your intermediate that makes the product on the left the more favorable product. Does that make sense? Okay.
Under cold temperatures, we would favor the other one.
No, in this case, you're kind of stuck getting the halogenation at the more substituted carbon, simply because that's the much more stable intermediate. Yeah. All right. Let's take a look at alpha halogenation under basic conditions. So we just covered the full acidic mechanism. All right, under basic conditions, it's pretty similar. I'm going to use a different ketone. However, we use sodium hydroxide instead of acid, and we use Br2. Are we going to install the bromine at this green position over here? Or the blue position over here? Blue position, why? Yeah, you can't form the enolate on that green side without going through a Texas carbon. So in this case, even though that green carbon's more substituted, the halogenation has to occur at the blue position because you can't form an enolate at that other side.
Is NaOH strong enough in this case, or do we need the LDA?
That's a good question. So in this case, you could use LDA if you wanted, or you could use sodium hydroxide. Because the equilibrium is somewhat unimportant, I guess I should backtrack a little. Even if you only have a small percentage of your enolate, that's enough to act as a nucleophile and drive the reaction to completion. So it doesn't have to all be enolate, even a small percentage will drive this reaction. All right, so we get a bromine installed right there. And just like we saw before, this can often result in overbromination as well. Oops. The mechanism is very straightforward. It's just like you'd expect. So I'm going to draw in these alpha protons. We've got our two methyl groups. We've got sodium hydroxide, which, yeah, it's not the world's greatest base, but a small fraction of the equilibrium will form the enolate. And now that we've got bromine around, the carbon will act as the nucleophile. And you'll get monohalogenation, or if you keep on pushing it, you can get dihalogenation. Does that make sense? I know it's kind of repetitive, but it's good to draw them all out. All right, now we get to do a kind of goofy variant of this. This is alpha halogenation of carboxylic acids. This reaction is referred to as the Hell-Volhard-Zelinsky reaction. Oops. It's a pretty old school reaction, and there's a lot of variants based off of it, but it's a classic way to halogenate carboxylic acids. So let's take a look at the reaction. We've got our basic carboxylic acid drawn. The first step is to treat it with phosphorus tribromide. What will that do? Yeah, it'll turn the OH group into a bromine, so we'll form an acyl halide, right? We saw that last chapter. It's pretty reactive, and whenever we do this reaction, you can also think of this as being in equilibrium. with the enol form, right? Because we're under acidic conditions, or we spit off acid in the PBr3 reaction. This looks like a pretty unstable enol to me. And then if you treat this with bromine, just like we saw in the previous reaction, you can halogenate at that alpha position. So this oxygen will clamp down electrons. This carbon will attack the bromine and kick off a bromide. And then typically you can have a deprotonation event occur. And you can get your alpha brominated acyl halide. What happens if we treat this with water? Will it form an alcohol, or what will happen? Carboxylic acid. We know if we treat an acid halide with water, we just go back to our carboxylic acid, right? So I'm not going to draw the full mechanism for that, but it's good review from last chapter. And now that we have that, we can do all sorts of unique chemistry with the carboxylic acid functional group. Make sense? All right. Let's see, do we have enough time to do one more? Let's do a practice reaction. We'll call this the end of today's lecture. The question is, how can we go from this alkene to this alpha halogenated carboxylic acid? So propose a synthesis. What's that? This isn't the pod. It's similar. So the pod, you guys, make sure you read the thing I underlined where I said you had to start with alcohols containing 2 carbons or fewer. Oh, it says 4? All right, that was a typo on my part. I'll let you use 4 carbons or fewer. Shoot. All right. If you want a challenge, do it with 2 carbons. You'll get bragging rights if you can do it with 2 alcohols. Or 2 carbon alcohols. No, it's just an ego boost. All right. So let's do this retrosynthetically, right? We know we can get to this compound from the carboxylic acid. Now the question is, how can we get from that alkene to the carboxylic acid? So we can't oxidize the alkene directly to a carboxylic acid. What was that? Okay, so I heard somebody say, what if we made the carboxylic acid from an alcohol? That would mean the alcohol this must have started from would be this. The question is, how can we get from this alcohol from an alkene? Can we do that in one step? Yeah, exactly. So let's kind of piece this together going forwards now. All right, we'll fill in all the reagents. And then we've got alpha halogenation. Okay, let's plug in the full forward reaction with all of its reagents. First step, what do we need? Yeah, we can't use straight acid because it's anti-Markovnikov, so BH3, THF, and then what's step 2? So H2O2 and NaOH. So we've got to use peroxides. All right, and then how do we oxidize the alcohol to a carboxylic acid? Chromic acid, right? We can't use PCC because that will stop at the aldehyde. H2SO4 and water. And then the last step, what do we need? PBr3. Two would be Br2. And then if we want to quench it at the carboxylic acid, we just treat this with water. All right, so now we can start functionalizing molecules to a greater degree. All right, tomorrow when we come in, we'll continue on and we'll discuss another alpha halogenation reaction called the haloform reaction.